Welcome to For the Love of Physics podcast. We are Mr. Jager's assistant.
Hello, everyone.
And a special warm welcome to all the Ishik Boys high school students, especially those in Mr. Jager's class.
Great to have you tuning in.
Today, we're doing a deep dive into something you see, well, probably every day. Curved mirrors.
That's right.
We know you've got the basics down with Mr. Jager, so we want to explore how these mirrors are different from flat ones, how they bend light, and how they shape what we see.
Yeah, from seeing yourself in the morning to, believe it or not, looking at distant galaxies.
It's all about how light follows some pretty cool rules, not tricks, to make these images.
You might think mirrors are just, for checking your hair, but today we're going to see they do so much more.
Okay, let's unpack this. Curved mirrors.
Yeah.
You definitely see them around.
Oh, for sure. Maybe without even realizing it.
Yeah, they're not like your standard flat bathroom mirror. We'll focus on the two main types, concave and convex.
It's a bit like comparing a flat road to a really winding one.
How so?
Well, light takes very different paths, and you get very different outcomes depending on the curve.
Gotcha. Okay, first up,
Yeah.
concave spherical mirrors.
Right.
The easy way to picture this, think of the inside surface of a spoon. It curves inward.
Caves in.
And the key thing here is that these mirrors converge light. They bring the incoming light rays together at a point.
Exactly. Focus them.
Like, remember those small round mirrors people sometimes have on dressing tables? The ones that magnify?
Oh yeah, the makeup mirrors.
If you get right up close, your face looks huge,
Yeah.
right? Much larger than normal.
Definitely.
Well, that's a concave mirror doing its thing.
It's amazing, isn't it, how it just seems to zoom in?
It really is. But, and this is where it gets kind of weird and interesting,
Uh-oh.
if you back away from that same mirror, like step further back,
What happens?
your image can actually flip. It can appear smaller and totally upside down.
Whoa, so it goes from magnified and upright to smaller and inverted just by changing distance.
Exactly. It's not magic, it's physics. How does that work? What's defining that change?
Okay, good question. To really get why the image does that flip, or why it magnifies, we need a few key terms about the mirror itself. Mr. Jager probably covered these.
Let's recap them.
First, imagine the mirror is part of a giant, complete sphere.
Okay.
The radius of that whole sphere is called the radius of curvature. We use a capital R.
So R tells us how curvy the mirror is.
Precisely. And the center of that imaginary sphere, that's the center of curvature, or C, it's a distance R away from the mirror's surface.
Got it. Radius R, center C. What else?
Then there's the principal axis. Just picture an invisible straight line running right through the center of the mirror's surface and through C, the center of curvature.
Like an equator line through the middle.
Sort of, yeah. It's the main line we use as a reference for how light rays travel. These terms, R and C and the axis, they define the mirror's geometry.
Okay, so those physical properties dictate how the light bounces off, which leads to the image we see. Now, you mentioned images. What about this idea of a real image? How is that different from just, seeing my reflection?
Yeah, that's a really important distinction. A real image forms when the actual light rays, after reflecting off the mirror, physically cross each other or converge at a specific point in front of the mirror.
In front, not behind, like in a flat mirror.
Exactly. Think about your bathroom mirror. Your reflection looks like it's behind the glass, right? You can't, put a piece of paper back there and catch the image.
No, definitely not.
But a real image, because the light rays actually meet in front, can be projected onto a surface.
Oh, like a movie projector.
Precisely. A projector lens creates a real image on the movie screen. That's the key difference. Real images can be projected.
That makes sense. And we can actually figure out where these images will form, right? Using math.
We absolutely can. There's something called the mirror equation. Now, we're not going to plug in numbers today.
No calculations, promise.
Right. But the equation itself is super useful. It connects the object distance, that's how far the thing you're looking at is from the mirror.
Okay, object distance.
The image distance, that's where the image actually forms.
Image distance.
And the mirror's curvature, often using that radius R we talked about, or something related called the focal length.
So this equation lets physicists and engineers predict exactly what will happen.
Yep. It's fundamental for designing anything with curved mirrors, like telescopes or even some medical instruments.
And you mentioned focal length. What's that?
Good question. Imagine light rays coming from something really, really far away, like starlight. Those rays arrive essentially parallel to each other.
Okay, parallel rays.
When those parallel rays hit a concave mirror, they all reflect and converge, they meet at one special point. That point is called the focal point, labeled F.
The point where parallel light focuses.
Exactly. And the distance from the mirror's surface straight along the principal axis to that focal point F. That's the focal length, little f.
Okay, F is the point, F is the distance.
You got it. And for spherical mirrors, there's a neat relationship. The focal length f is exactly half the radius of curvature r, so f equals r2.
Oh, simple. So if you know how curved the mirror is, you know its focal length.
Pretty much. It's a key property. And knowing f helps predict the image, including its size.
Which brings us to magnification.
Right. Magnification, usually m. It tells you how much bigger or smaller the image is compared to the actual object.
So if m is 2, the image is twice as big.
Yep. If m is 0.5, it's half the size. If m is less than 1, smaller image, greater than 1, larger image.
Okay. But what about the upside down thing?
Ah, the sign of m tells you that. If the magnification m is negative, it means the image is inverted upside down.
Negative m means inverted.
And that usually happens with real images formed by concave mirrors. If m is positive, the image is upright, the same way up as the object.
Positive m upright. Got it. So the equation gives numbers, but how can we visualize this?
That's where ray diagrams come in. They're like drawing maps for light rays. Yeah, you draw a couple of specific, easy-to-track light rays leaving the object, see how they reflect off the mirror according to the rules of reflection, and then see where those reflected rays cross.
And where they cross, that's the image.
That's where the image forms. Ray diagrams are great visual tools. They help you see why the image is where it is, whether it's real or virtual, upright or inverted. They confirm what the mirror equation tells you.
Cool. So putting it all together for concave mirrors, the image really changes depending on where the object is, doesn't it?
Absolutely. It's all about the object's distance compared to the focal length f.
Okay, so if the object is far away, like further out than the focal point f,
then you get a real and inverted image. It might be smaller or larger depending on how far, but it's real and upside down.
Okay, what if the object is right at the focal point f?
Ah, interesting case. The reflected rays end up parallel, so they never converge to form an image. Or you could say the image forms infinitely far away. Basically, you don't see a clear image.
Okay, but what about really close? Closer to the mirror than the focal point, like with that makeup mirror example.
Exactly. If the object is inside the focal length, closer than f, the mirror acts as a magnifier. The reflected rays don't converge in front, they actually spread out.
Spread out, so no real image.
Right. But if you trace those spreading rays back behind the mirror...
they look like they come from behind it.
Precisely. They appear to come from a point behind the mirror, forming a virtual image that is upright and magnified.
That's the big reflection you see in the makeup mirror. Virtual, upright, and magnified.
You got it. Concave mirrors are pretty versatile.
Okay, let's switch gears. Flip the spoon over. Now we're talking convex spherical mirrors.
Right, the outside of the spoon. These curves outward.
Bulging out towards it.
Yeah. And their effect on light is the opposite of concave mirrors. Instead of converging light,
they spread it out.
Exactly. They diverge the incoming light rays after reflection.
Okay, where do we see these?
Think about the passenger side mirror on a car.
Oh yeah, the one that says objects in mirror are closer than they appear.
That's the one. That warning is there because it's a convex mirror.
Why does it make things look further away?
Because it curves outward, it reflects light from a very wide angle. It gives you a broader field of view, lets you see more of what's beside the car.
So you see more area.
Right, but the trade-off is that it makes everything within that view look smaller. And smaller things tend to look further away to our eyes.
Okay, so wide view, but smaller images. That makes sense for seeing traffic. Any other examples?
Sure. You often see large, round, convex mirrors mounted high up in the corners of shops or warehouses.
The security mirrors.
Exactly. They give staff a wide-angle view of the aisles to watch for shoplifters or just keep an eye on things. Again, it's about seeing a large area, not about magnification.
So if concave mirrors can make real or virtual images, big or small, inverted or upright, what about convex mirrors? Are they simpler?
Much simpler in terms of images. With a convex mirror, the image formed is always virtual.
Always virtual, meaning it always appears behind the mirror.
Always behind the mirror. The reflected rays always diverge, so you trace them back. And the image is also always upright.
Always upright, never inverted.
Correct. And finally, it's always smaller than the actual object.
Virtual, upright, smaller. Always. That's easy to remember.
It is. And because the focal point is effectively behind the mirror where the virtual rays seem to meet, its focal length f is considered negative when you use the mirror equation.
Okay. Negative f for convex. Got it. All right, one last type to touch on quickly. Parabolic mirrors.
Ah, yes, these are special.
We mentioned spherical mirrors, concave and convex. Is there a problem with them?
Well, problem might be a strong word, but spherical mirrors aren't quite perfect at focusing light, especially if they're large.
What do you mean? We said concave mirrors focus parallel light at the focal point F.
They do, mostly. But it turns out for a perfect sphere, only the light rays hitting very close to the center, near the principal axis, converge precisely at F.
Only the ones near the middle.
Yeah. Rays that hit the mirror further out towards the edges actually get focused slightly closer to the mirror than F.
Oh, so not all rays meet at the exact same spot.
Correct. This causes the focus point to be a bit spread out, a bit blurry, instead of a perfect point. It's called spherical aberration.
Spherical aberration. Sounds like a headache for telescope makers.
It can be, yeah, especially when you need really sharp, clear images.
So how do parabolic mirrors help?
This is where their shape is brilliant. Parabolic mirrors aren't shaped like part of a sphere. They're shaped like a parabola. Think of the path a ball takes when you throw it.
Okay, a different curve.
A very specific curve. And the amazing property of a parabola is that all parallel light rays coming in, no matter where they hit the mirror surface, near the center, near the edge, anywhere, they all reflect perfectly to converge at one single focal point.
All of them. No more blurriness.
Exactly. No spherical aberration. You get a much sharper, brighter focus.
Wow. Where are these used?
Lots of places where you need precise control of light beams. Think about a flashlight or a car headlight.
Yeah. The reflector dish behind the bulb is often parabolic. They put the bulb filament right at the focal point. So the light goes out from the bulb, hits the mirror, and reflects off in a strong parallel beam. That's why headlights are so bright and focus straight ahead.
Clever. What else?
Big telescopes, especially reflecting telescopes that use mirrors to gather light. Think of giant observatory telescopes or even the Hubble Space Telescope.
They use parabolic mirrors.
Absolutely. They need to collect faint light from incredibly distant stars and galaxies and bring it to a perfect, sharp focus to create those amazing images. Parabolic mirrors are essential for that kind of precision.
Even radio telescopes, those huge dishes.
Yep, same principle. They use that parabolic shape to collect faint radio waves from space and focus them onto a receiver at the focal point.
So that shift from a spherical shape to a parabolic one makes a huge difference in performance.
A massive difference. It's a great example of how a specific geometric shape solves a physics problem perfectly.
Fantastic. So that's quite a tour of the curved mirror world.
It really is. We looked at concave mirrors, curving inward, converging light, able to magnify up close or create real, inverted images further away.
With key points like C, R, and F defining how they work.
Then convex mirrors, curving outward, diverging light, always giving virtual upright, smaller images, great for wide views.
Like in car mirrors or security mirrors.
And finally, parabolic mirrors, the perfect focusers, getting rid of spherical aberrations, crucial for things like headlights and telescopes.
Bringing light together just right.
So next time you look in a mirror, especially if it's not just a flat one.
Take a second. Think about the physics. Is it concave?
Convex?
What kind of image are you seeing and why?
Yeah. And here's a quick thought for you, a mini quiz maybe. Can you think of another everyday object, maybe one we haven't mentioned, that uses a curved mirror?
Could be concave, could be convex.
How does that mirror help in whatever that object does? Give it some thought. Well, that wraps up our deep dive on curved mirrors for today.
I hope you found it useful.
Stay in contact with your physics teacher.
Stay creative.